Okay, great. So we continue right now with Townsend and Escardo's patch.
Right. Well, good morning, everybody. Lovely to be here. Lovely. It was highly speculative. I just assumed there'd be lots of other more experienced people who would be speaking, but I happen to have been with Martin back in 95, 96. We both worked on the patch construction, and I thought this would be an excellent opportunity just to tell the story of the patch construction. I've only got, if it would be possible to move that, that'd be great. I've only got 10 slides to go through, so hopefully I'll leave some time for questions at the end. My first slide, I just want to make sure we're well motivated. I'm going to tell you what is the patch construction, what are the categories involved, what's it about. Then I will describe Martin's construction, which is particularly simple and nice, and I will contrast it to my construction at the time, which wasn't particularly simple and nice. Then I'll take a little bit of a step back, and I'll describe how we can construct stably locally compact locales, and at the time how we were thinking about that in terms of our spatial intuition. And then I'll go back to the motivation in terms of just discrete posets, so everybody should be able to follow that because it's not got any topology. And then I'll show how that line of reasoning allows us to reconcile these two approaches to patch. So at the end of the day, they looked different, but they turned out to be the same. Finally, time permitting, I'll give an application of Escardo's patch, which I don't think is widely known, and I'd be very happy to get some feedback on it. So what are we talking about? Well, the patch construction is a way of getting a compact Hausdorff locale from a stably locally compact locale. So I'm going to assume you know what a compact Hausdorff space is, and I'm hoping you understand what a compact Hausdorff locale is. The categories are the same there, but when we're doing locale theory, we're trying to think constructively. Explicitly, we're trying to do everything relative to an arbitrary topos. So I'm assuming you know compact Hausdorff locales, but you might not know what the stably locally compact locales are. Well, here we have a bunch of equivalent definitions. They are the continuous frame, so continuous lattices, they're compact. They have a meet stable way below relation. That's one characterization. Take that as your definition if you like. They are also described as the injectives in the category of locales with respect to the flat inclusions. They are the retracts of the coherent locales. And when they were introduced spatially, they've been described intuitively as reasonable, not necessarily compact Hausdorff spaces. And to introduce the patch, an example of a stably locally compact locale is a compact Hausdorff locale. So compact Hausdorff locales go into stably locally compact locales, and the patch is a co-reflection. The experts should be complaining because I haven't said anything about the morphisms there. So to be precise, I should say something about the morphisms, but just for simplicity, it's a way of getting from a stably locally compact locale back to a compact Hausdorff locale. And you should be interested in these things because there's lots of different descriptions of the same object. So intuitively, I think you should be drawn in. Another way of looking at the patch construction is seeing it as an equivalent. And this is, when I was working under Vickers, this is sort of more where we were coming from, seeing it as an equivalence between stably locally compact locales and compact Hausdorff posets. Could we actually represent compact Hausdorff posets as stably locally compact locales and set up an equivalence? Moreover, could we do it localically rather than just in the spatial case? And it's important to point this out because this restricts to Priestley duality. And so it relates to a well-known and important duality. The action in that case, when you're looking at spectral spaces in terms of stably locally compact locales, the action there of the patch is taking the free Boolean algebra on the compact topos. So that's to set the scene in terms of what stably locally compact locales are. They're not as scary as you might think if you're new to the subject. They're very important. So what did Martin show me back at Imperial College when we shared an office? He showed me this, basically, that the frame of opens of the patch of Y, it can be described very simply. It's simply all the nucleuses that preserve directed joins. Now, if you're new to the topic, you're like, oh, okay, great. You've told me how to define that co-reflection. I can just work through all the detail. But what bothered me is its contrast to my description. As I said, I was working on the problem coming at a slightly different angle. Well, take the free Boolean algebra on omega y, take its ideal completion, then take the frame itself, embed it in that ideal completion, take the frame, take its Scott open filters, and then embed that in the same thing, and then take the whole frame that's generated by those objects. So I was very, very pleased with what I'd done, but clearly, in contrast to that, was like, that's not nearly as elegant. Now, I did notice straight away that Martin's patch was contained in the collection of pre-frame morphisms from omega y to omega y, and that's a triviality. What do I mean by a nucleus? A nucleus is something that preserves finite joins, and therefore, if you're preserving finite joins and you're preserving direct joins, you're embedding, you're a pre-frame. That's a definition of a pre-frame homomorphism. It preserves directed joins and finite meets. Sorry. Yeah. That's the definition of pre-frame morphism. And yeah, and we were thinking about pre-frame morphisms at the time. So taking the Scott open filters, for example, is taking the pre-frame homomorphisms away from the frame to the sub-object classifier. So what I want to now do is tell the story of where we were coming from, and that will motivate the story as to how we sort of come together. So where we were coming from is that I had proved that the compact Hausdorff relations on X for any compact Hausdorff locale were the same thing as a pre-frame endomorphism. So I didn't mention it earlier, but compact Hausdorff locales form a regular category, so we can define a relational composition in them. And what I proved was that those relations correspond to pre-frame endomorphisms. I say I proved. What really happened was that Steve told me, and I spent 3 months proving it under his direction. So really, this was Steve's idea, but it was central to my thesis. And the example that, again, I proved, but really Steve told me, was that under that relationship at the top there, which I can't point to, but I think you know what I'm pointing to. Under that relationship, we can take a less than or equal to is idempotent with respect to relational composition, and therefore it corresponds to an idempotent pre-frame homomorphism. I can take its fixed points. I get a stably locally compact locale. With this understanding of that pre-frame endomorphism as a relation, I can see I've got a spatial intuition as to what the opens are that I've described. They're just the topologically closed and the upper closed with respect to relation. So we had some sense of going from the compact Hausdorff posets to the stably locally compact locales. But what I couldn't do is go in the other direction in a nice, neat way. And there appeared to be two different ways of doing it. So next slide is if only we had paid more attention to our discrete motivation. So going up, let's see if I can point. Which button is it?
The red one.
Red one at the top. Yeah. So where was this thing coming from? Other than Steve had told me, it was really coming from, it was really the compact Hausdorff dual of this relation. So this relation, I'm hoping people are familiar with, because now you can forget all your topology and your compact Hausdorffness. You've just got a poset, or you've just got a set in the first example there. So the power set of relations on L times L for any set is the same thing as a sublattice arbitrary join preserving function from the power set to itself. That's easy to see. And the relational composition in that context goes to function composition. So you play the same trick and you get the set of upper closed subsets of your poset as your discrete dual to what you're doing on the compact Hausdorff side. Well, U of L is just the frame of opens of the ideal completion of L. So on the discrete side, you're looking at what is well known, the algebraic DCPOs. So in that context, once you're thinking, okay, well, I'm looking at the discrete, on the compact Hausdorff case, on the compact Hausdorff side, I'm looking at the parallel for the algebraic DCPOs. In order to back out the set from the algebraic DCPO, I just need to take the compact elements. But for that to work, I need the points to exist. And that's obviously not going to work on the compact Hausdorff side because the points don't exist constructively on the compact Hausdorff side. And the punchline is really contained in this proposition that wasn't proved later. And I'd be very curious if anybody's kind of seen it. It's a completely trivial proposition. If I've got a partially ordered set and I take the set of all lower closed on the left and upper closed on the right subsets of it, I can define an endomorphism of that by intersecting with the diagonal and taking the left closure, the lower closure on the left and the upper closure on the right. And it turns out that the power set is embedded in this set of relations via splitting that idempotent. So actually, we didn't need, on the discrete side, it's actually quite obvious how to do the construction by just using sublattice homomorphisms and splitting this idempotent. And in fact, we can do exactly the same thing on the compact Hausdorff side because we have this relationship between relational composition and preframe homomorphisms. You can translate exactly what you're doing on the discrete process onto the compact Hausdorff side. But in this case, you're using this relationship on the opens, your intersection of diagonal, take lower and upper closed, and you're recovering omega x. You're getting the patch construction back. So you're going from compact Hausdorff. We knew how to go from compact Hausdorff in order to get stably locally compact. The problem was going back. So the problem was recovering our x from our x bar. The omega x, the patch of the omega x bar can be found as embedded in that. Well, although I haven't labored the point when I introduced the stably locally compact locales, in exact analogy to the algebraic DCPOs, they also form a star autonomous category. So star autonomous categories, finite vector spaces with duals, they form a star autonomous category. So you might be familiar with if you take the dual and you tensor it, then you get the same thing as linear maps. Well, exactly the same thing happens once you restrict within the stably locally compact case. And so finally we had this not only did we have the relationship here, so we knew why the preframes were corresponding. So at the beginning I was going, oh, I've got these preframe morphisms from Martin's description. In my description, I seem to have these Scott open filters, which are these, and the elements of the frame itself. How come they're the same thing? Well, it's just a consequence of the star autonomous structure on the stably locally compact locales, and they're all subsumed into any description you like of this frame of opens. So actually, it was quite obvious why there were very many different carrier sets available. So having said all that, what I think is an interesting application is that we're able to make I've only talked intuitively about a kind of parallel between the compact Hausdorff and the discrete side. Now, you can't take that parallel too far because you've got toposes on one hand, and certainly the compact Hausdorff things are not toposes. But a lot of the stuff that I've been working on over the years is about developing the regular fragment of logic within this context. And so a natural question arises as to whether we can find a regular statement within the regular fragment of logic that isn't parallel between the two, or do we actually think all regular statements are parallelizable between compact Hausdorff and discrete? And in fact, Martin's example by this proposition gives us something that isn't parallel under the two. So to be explicit about that, there's a proposition there. Let's say R is contained in the diagonal. It's idempotent. It's lower closed on the left and lower closed on the right. Then those conditions mean that actually it must be determined by its restriction to the diagonal. And the reasoning is relatively simple, given everything I've said. There's some canonical isomorphisms I'm not explaining here, but if you have that third condition of lower closed on the left and up closed on the right, then it must be contained in the frame of opens of the corresponding stably locally compact. The conditions 1 and 2 then restrict to the stably locally compact. So you know that the corresponding nucleus, the corresponding preframe homomorphism is in the patch. So, so you only have to have those two conditions to be in the patch, thanks to Martin's description. But you've also been given a description of the patch just now in terms of the restriction to the diagonal. So you know that the relation must be restricted to the diagonal. And this is in contrast to the discrete case, because in the discrete case, you can just think of the strictly less than relation, which satisfies all these properties, and certainly doesn't restrict to the diagonal, because once you intersect the strictly less than with a diagonal, you get the empty set. So, yeah, I found that very intriguing. Still, I haven't looked at it for about 10 years. I sort of took it out to have a look for this talk. I still find it a little bit doubtful, because if that is the case, it's a great application of it, but also it'd be true of compact Hausdorff spaces. So I'm a little bit skeptical about where we've got to in this line of reasoning. But for me, that's, not only was the description that Martin gave a heck of a lot more simpler than mine, but it allowed us to see why there were lots of different constructions of the patch. And I think it's suggesting here facts about how compact Hausdorff things and discrete things should really be related to each other. I'm not sure how much time I've spent, how much.
About 3 minutes.
Oh, I got 3 minutes. I'll just briefly, apparently it's very good practice to tell everybody tell you what you're going to tell them, tell them it, and then tell them what you've told them. But maybe you don't need to advertise it so much. I don't know. Okay, there should be a natural interest in stably locally compact locales. I know when people study it, it's kind of like you get to coherent locales, and then it's like it's a bit much. But they really are closely related to compact Hausdorff spaces, and also you can relate them back to Priestley duality and therefore stone duality. So it's one thing I wanted to convey is it's not a terribly obscure thing. Escardo's patch is particularly simple and contrasts to other constructions, which I labored at the beginning there. And it was not until later that we discovered why there were so many different carrier sets existed. And in fact, the patch construction, in my mind now, is, I actually literally think on the discrete side, it's just a process of backing out the power set from the set of lower closed on the left and upper closed on the right subsets. And there's, although I've introduced an element of skepticism here because I kind of reviewed it in the last few weeks and I'm not 100% sure, but I believe there is a application of patch construction which actually provides us an example of a statement, a regular statement that is asymmetric with respect to discrete and compact Hausdorff duality. I think that's probably more than enough from me. Thank you.
For answer of a question,
Please, yeah.
So once I was in our office and the phone rang and then Steve said, is this there? And I said, no, please not here. And then Steve said, by the way, the paper that you put under my door, can you generalize this from spectral locales to stably locally compact locales? Which is what you were talking about, and I asked him, what is a stably locally compact locale? And then he told me over the phone.
Yeah.
And then I managed to do this.
Yeah. I'd actually, because Steve did mention that, I'd completely forgotten that. But yeah, now that you're reminding me, yes, there was, yeah, I mean, and I think Carragus also had a similar description in terms of doing it at the, because you talk about doing it at the sort of Priestley duality level. And that was also what I was working with. And again, just did the ideal, did the free Boolean algebras. So yeah.
Anyway, I've got a question about history. Do you know who coined the
yeah, I believe the paper is Hoshta 69, because when I was preparing this talk, I was going to give a long history on patch. And it's not particularly because we associate it with Priestley duality, and I think that's partly because how it's written up in stone spaces, but it's not actually particularly part of the Priestley duality. It's about the relationship between spectral spaces and ordered stone spaces.
Regarding the question.
Sorry, that's the one that proved that spectral spaces were spectral.
I don't know, sorry. I can go to this level, which is quite impressive, but I can't go to that level. I don't know, because I was just looking at it very briefly in terms of the history as to where the patch came from. So the patch construction is, yeah, you on spectral space, you take the compact opens and take their jewels and then generate something. I think that came from there.
The name patch may come from that paper, but I think the patch is probably older than that.
Okay.
And maybe I can confirm this. The little book by Nachting from compact out of older traces from 1946 or something like that.
Okay.
Yeah.
Oh, okay. That's quite interesting. If there was something in Nachben. Yeah. Yeah. There's a whole other.
Brazilian, by the way.
Yes. I know. Who was Brazilian? Yeah.
That's a very important fact.
Yeah. Yeah. So there's a lot of. I mean, there's obviously given the time skirting over a load of things, but if you haven't, the kind of the interaction between the order and the topological thing, a lot of the work have been done by Nachman, just in summary. Was there I don't know if there's time.
Maybe one more.
One
question. It was the same question.
Oh, all right.
All right. So
Okay.
Looks like our bigger speaker again. Thanks very much. All right. We're gonna try this.
Yes.
Okay. So the next.
You can stop the recording here.
Yeah.
Start filming.
Next.